Hello, class. All right, today we're going to be doing activity 29, constructing functions, and that is on page 395. So please get out your book, open it to page 395. While you're doing that, I'll read you a story. Wind turbines create energy from the power of the wind. Turbines can be small and power a home or a small building, or they can be large and contribute power to an entire power grid. A large group of wind turbines are run by the Tennessee Valley Authority on Buffalo Mountain near Oak Ridge, Tennessee. There's a picture of them. You've seen these driving through like the Altamont Pass. I don't know if you remember, probably not. But they used to have all sorts of tiny little turbines, and they replaced them with these monsters. These are incredibly large. If you get up close to them, this little part here, that the hub of the spinning part, is like the size of an entire train car. They're enormous. So the Buffalo Mountain holds 3 older turbines that are 213 feet tall and have blades that are 75 feet in length. Each of these older turbines generates 660 kilowatts of power per hour when they are producing at their maximum. There are newer, larger turbines as well that have a height of 260 feet with blades that are 135 feet long, and they create 1,800 kilowatts of power per hour. Determine how much energy in kilowatt hours each of the newer turbines generates in a 24-hour day. So the things that we're picking apart in here, they said newer turbines, so I'm going to use this information. They want to know how much power they generate in a 24-hour day. So the 260 feet blades, that's not going to help me figure out how much power. That they're 135 feet long, that's not going to help me figure out how much power. That each turbine creates 1,800 kilowatts of power per hour, that's going to help me. So in a 24-hour day, if this is per hour, this is in 1 hour, then in order to figure out how much it's going to be in a 24-hour day, does everybody agree I can just multiply this by 24? In 1 hour, it's creating 1,800 kilowatts. 2 hours, 2 groups of this. 3 hours, 3 groups of this. Group sub is multiplying. So I can break out my handy calculator. And I got 1,800. Trying to see where you can see that. Times 24. So it looks like 43,200. So 43,200 kilowatts per day. All right, let's move on. Page 396. Page 396 says, write a function to represent the amount of energy generated by a newer turbine for X number of hours. Be sure to define the variables you use. Well, they already told us that X equals the number of hours. And Y, since we're generating a function to represent the energy generated, Y would be equal to the amount of energy in kilowatts. And since it's hours, our equation is going to be Y, the amount of energy, is equal to 1,800 times X, right? So that's my equation. Explain why function you wrote is directly proportional. So this is directly proportional. Remember, we had 2 criteria for directly proportional. One was that it be linear. And this equation is linear, so it's linear. And number 2, the y-intercept has to be equal to 0. And for this equation, it has a y-intercept equal to 0. All right. Unfortunately, wind turbines only produce at top capacity a small range of wind speeds. It has been suggested that wind turbines only produce 40% of the power they theoretically should. And that makes sense because the wind isn't blowing really strong all the time. Sometimes it blows stronger and it makes more power, and sometimes it's not blowing at all and it doesn't make any power. How much energy would be generated in one 24-hour day with the turbines producing only 40% of the expected power? Now, we had that number. For a 24-hour day, we said 43,200 kilowatts in a full day running at full power. So what we want is 40% of this number. Do you guys remember your percents? It's been a while. So 40%, we could write a proportion. 40 over 100 is equal to x over 43,200, right? Percent over 100 is equal to the part over the whole. So this 100% is everything, and 43,200 is all of the power. 40 is just the part that we want, 40%, and x is the part of the power we're going to have. And then we could cross multiply this, and we get 100x is equal to, I'm going to have this times 40, which gives me this, 1728000. Divide both sides by 100. And I get 17280. And the units of that are kilowatts. So that's all we're going to get. We're not going to get the full 43,200, or we shouldn't count on it anyway, because this may not be that windy. Rewrite your function to represent the power that wind turbines produce with only 40%. So my equation now would be y equals 17280 times x. Although, if I do it that way, x is the number of days, not the number of hours. Up here, we said x was the number of hours. But we're going to change it to days because I'm looking down at this table. And in this table, they're using days. Does that make sense? Sure it does. So that's a much bigger number. Is it a much bigger number? Yeah, it is. All right. So now x equals days and y equals total power. All right. So now we want to complete the table. Please pause the video and complete the table. When you're done completing the table, go ahead and start the video again. All right, welcome back. So for 30 days, you should have gotten 518,400. For 60 days, you should have gotten 1,036,800. For 90 days, you should have gotten 1,555,200. For 120 days is 2,073,600. 3,110,400 and 6,307,200. All right, moving on to the next page. We're on page 397. Page 397. We are now going to graph our table that we did in the last one. So the table has the number of days as the input, and the power generated as the output. And these are enormous numbers. It would be very hard to graph these. But look at the y-axis, how they labeled it. So they labeled it power generated in millions of kilowatt hours. So if I take a look at my table here, I can change these into millions. Let's do that. So this is going to be 1.0 million. Does everybody see that? Because this is 1,036,000. So if I'm rounding to the millionths, or one digit to the right of the millionths, this zero stays a zero because this number is smaller. And this is I'm rounding to the 5. It's got a 5 to the right, so we'll go up, 1.6. Here I'm rounding to the 0. 7 is bigger than 5, so we'll go up. So 2.1 million. Here we have 3.1 million and 6.3 million. Take a minute, pause the video. What's this guy going to be? Yeah, that guy's going to be 0.5 million, right? Because there's 0 millions, 581 thousands. So these are the numbers we're actually graphing because of the way they set up their axis. So let's do that. So for 30 days is going to be halfway between 0 and 60. Why did they count by threes? I don't know. But halfway is right there. So 30 days for the input, and then half is going to be about there, right? Halfway from 0 and 100. For 60 days, we're at 1.0, so that's a nice one to graph. For 90 days, again, halfway between 60 and 120, we're going to be at 1.6. So that's 1.5, 1.6 will be up a little. For 120 days, we're at 2.1, a little bit above 2. For 180 days, we're at 3.1. So there's 3.1 would be a little bit above. And for 365, so this is 360. They're counting by, what are they counting by? 20s. So 365 is going to be right here, I guess. And we're up to 6.3 million. 5, there's 6, 6.3. Well, that would be 6.5, so 6.3 maybe here. All right. Well, that was tricky to graph. And is it linear? We know that it should be linear based on the equation we started off with. I'd say that's pretty good given how funky their system is. We know it's directly proportional, so it should go through 0, and it does. So 0 days running those turbines, 0 power generated. What is the domain and the range of this function? Well, we're going to assume that we turn this turbine off after 360 days. So this is our graph. So the domain of the graph are all the x values that are right underneath this graph. So if I drop straight down, we went to 365 here, remember? So 365 is the biggest number. And then it goes all the way down to 0. 0 is the smallest number. And it includes, so there's 2 different ways to do this. So if I use the table, I would say that the domain is 30, 60, 90, 120, 180, and 365, right? But we know that for the turbine to get to 60 days and generating 1 million kilowatts of power, it must have been also working on 59 days and 58 days and 54 and a half days, right? We're just finding data points at these, but this windmill's been running for the entire time. So the domain is going to be all the values of x that are bigger than 0. So the bigger part of this inequality is pointing at x. So x is bigger than 0, and x is also smaller than 365. So when you have data like this that's all continuous in a line without any breaks, then we're going to write the domain using inequalities to show it's all the numbers. So x is all the numbers between 0 and 365. This is the same thing as writing x is greater than 0 and x is less than 365. All right, how about the range? Well, again, the range, we're going to be looking at the y values. So now we're going to drag these across and look at what part of this y-axis is covered here. Hopefully you can see that we're starting at 0. And then the biggest number we had was 6.3 million kilowatt hours. So 6.3 is going to be our biggest value. Oops, million. I'm going to write times 10 to the 6th power for million. Do you remember that? So y is going to be all of the values between 0 and 6.3 times 10 to the 6th power, or 6.3 million. Is this function discrete or continuous? Well, I just said it never turns off, right? So there's data in between all of these points. Remember, continuous means that you're not jumping from one day to day 2. You also have 1.5 days and 1.3 days. And that is true. So the number of days can be split up into the tiniest of little pieces. And the power generated, you don't have to generate 1 kilowatt and then you jump to 2. You have 1.5 kilowatts and 1.1 kilowatts. So this is continuous data. And how would your equation change if the power is generated by all 18 of the newer turbines? Well, we would multiply our numbers by 18, right? The kilowatt by 18. So if you rewrite your function would now look like y equals 18. I'm not even going to do the math. 18 times 17,280 times x, where x is equal to the number of days and y is equal to the kilowatts of power. All right, hopefully this helped you out. Go ahead and give your homework a try, and I'll see you on Zoom today at 1 if you need help.